Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon. Okay, so in this video or in this class we will look at the chapter 4 for the computational fluid dynamics, which is that cover turbulence modeling. What we cover in this chapter basically consists of first is characterization of the turbulent flow, and then we have an Navier-Stokes equation to Rank's model, and we will look at on Reynolds stress tensor and for the closure problem, turbulent kinetic energy, a little bit on eddy viscosity, Newell treatment, and at the end we'll summarize with the guideline of choosing the turbulent modeling in our simulation. So what is the characteristics of turbulent? Here in this slide I write down the flow that inherently unsteady, in three-dimensional, and a periodic swirling motion, or we can say there's some fluctuation in the motion that result in missing or heat transfer or whatever flow. That's the one of the characteristic of the turbulence. So when we have the flow that consists of that kind of properties or the characteristic, we can say that the flow is turbulent. Wide range of scale length, which is one, or we have vortices or eddies, one of the what we call like a swirling, like flow like this. When we look at the simulation, this we call this eddy. Exists in all turbulent flow, from small to very large, either very small and very large, and all these things were sensitive to initial condition. That's why in our simulation we need to make sure we setting initial condition properly so that the result is better, and then the result is in good condition, because all these things or the turbulent characteristic very sensitive in initial condition. If we put the initial condition is in the wrong way or not correctly, so maybe we cannot have the good result in our simulation. So here a little bit explanation or basic explanation about the turbulent, which is that we have the fluctuation, this one, the fluctuation of u here, we have the fluctuation and the velocity in fluctuation. So for the this is versus time, to calculate or to simulate the turbulent basically is very difficult when we have the fluctuation of the velocity like this. So in the simple way, we can use, or we use the mean velocity, which is that we just take it the mean velocity of this fluctuation or average of this fluctuation to put in our equation for calculation the turbulent model. So we will look at this after this or the next slide in the equation of turbulent. This is the turbulent flow structure. So as I mentioned, we have some small structure, or maybe we have large structure like this. All start with the injection of energy with the large, we call it large scale eddy, and then flux of energy from one point to the other point. At the end, we have the very small eddies, and we have dissipation of energy. So this is the figure basically, the figure from the energy cascade taken by Richardson in 1922. And this we can see here from the point to entrance lines with this equation, the dissipating of energies occur at the end of the flow. So that's why important to us to make sure our setting in simulation correctly, so that the turbulent model that we choose is correct turbulent model, so that it can capture what's the problem that we want to simulate. A little bit revision of the turbulent flow. For external flow, we said that the flow is turbulent when the Reynolds number is more than 500,000 along the surface, and for along the obstacle, let's say we have the flow over the cylinder like this, and then the Reynolds number more than 20,000, we can say that the flow is turbulent. And the number, of course, I think all of you should know, that's the equation for a number, rho ul over mu. And for internal flow, let's say for example in the pipe or whatever, the turbulent flow occur when the Reynolds number is more than 2,300, like that, something like that. And for the natural convection, if we're talking about the convection, the Reynolds number, sometimes we for the natural convection, we do not refer to the Reynolds number, we refer to the Rayleigh number and also Prandtl number. So Rayleigh number over Prandtl number bigger than 10 to the power of 9, so the flow we consider as a turbulent flow. What the effect of the Reynolds number? So as I mentioned, let we take example for the flow over obstacle, or in this case the flow over the cylinder. When we have the Reynolds number less than 5, so there is no suppression occur, so very creep flow over the obstacle or over the cylinder. And when we increase the Reynolds number from 5 to around 15 to 40, we have a pair of stable vortices in the wake. We have vortices here, pair of vortices, but still in symmetry condition. Then when we increase the number, the laminar vortex start to generate, which is that this vortex. See, they start to generate, but it's still laminar. And then if we consider along the flow, we still have the similar pattern of the vortex. Then increase to 3 times 10 to the power 5, which is the boundary layer or at the transition region. We start to have the flow suppression at this condition, this area, and then increase the number laminar boundary up to suppression point, and then turbulent wake. We can start see the eddy occur here, and then for the turbulent, the suppression is lower than the laminar case. With the suppression occur here, but more or smaller than laminar vortex. So there's the condition where this example of the turbulent flow occur when the flow over the obstacle. This is the example of simulation for the flow with the different Reynolds number. We can see that the first one Reynolds number is 25. I can write down. Okay, 25. We have the okay, the flow for this case is to not have any vortex whatever. For the 50 also, we still have a little bit at the end. I cannot draw in the picture, so what I can put here for the second picture, vortex to start to occur. And then for the number 100, we have the higher vortex, and then when we increase more number, we can see that the laminar vortex straight occur higher than the third one. That's the example of flow over obstacle for the different Reynolds number. What's this? Dynamic control and flow of cylinder. This is a video. Okay, this is also the video. Then dynamics and control of the flow around the cylinder. We can see that the number we increase the flow. Okay, this one is the result for the simulation, which is the flow for the flow over that cylinder. At round number 48. Okay, this one, the second one. The flow is unstable, result to moving weight. Then this increase the drag. The drag will increase when we increase the number. Why does the weight form like this? Let's zoom in. Okay, what happened there? You can see near the wall the fluid slow down, and then the pressure increase as the far wall away. The push back the fluid back. Okay, this one you can see that the vector is in the opposite direction, and the expression of the bottom layer will occur. Of the upstream occur, more drag experienced by a cylinder. So the question is, can we prevent? So the three condition for suppression. The wall fluid constant, the wall fluid contact, which is at the no-slip condition, and we have the adverse pressure gradient and insufficient momentum. Okay, we look at this simulation for round number 180, and this one is zoomed for 600 speed. The small amount of fluid is sucked into the cylinder, and the wall remove the low momentum particle for this condition. Okay, let me on and try to look what happened in the flow for the condition 3, insufficient. Okay, we can see here flow does not reserve yet here, and then this one is the imaginary that the pressure occur on the surface of the cylinder or in the sphere. Okay, again we can see the pressure start to push more on the cylinder. There's the different location of the pressure occur in the cylinder due to the flow over the surface. So the strength of suction to eliminate the suppression is relatively constant, and non-uniform profile improves significantly upon uniform suction. So this is the one of the method to what we call to eliminate or to reduce the turbulence occur in some condition, which is that use the suction. What else? You can see here. Okay, for the this one is show the location, the different location of the suction in the cylinder that have the strong effect on the flow structure over the cylinder. So the optimized location suction varies predictably with round number. It's the different location of the suction. So the different location of suction or different angle of the suction will decrease the round number, so that we can prevent or we can control the turbulence occur on the surface. That is one of the dynamic to control the flow around the circular cylinder. Okay, so this one the example of the common model that researchers use to study the turbulent model, which is that the backward facing step. We can see the first the first picture. This the instantaneous velocity contour, which is that this one is the real one. So before this we have the fluctuation of velocity, and then we take the average to simple calculation or to simplify our calculation. This one is the real one, which with the fluctuation of velocity, and then when we take the average of the fluctuation, we got this kind of result. So it depends on what you want to study. If you want to only look at the simple one, look at the pattern or whatever, maybe the time average velocity contour is enough for you. But if you want to have more accurate, you need to what we call use this one, which is to consider all the eddies occur in the picture, all eddies occur in the flow. So you need to have more computational time and everything. So it's depend on what you want to study. Basically, for the time average velocity contour, or for the time average velocity, there's the common one used, and this one is acceptable for the certain case, or maybe I can say the most cases we can accept this kind of time average. Because so far, when the researcher or the engineers use the time average, they design something, then all the things is working properly. So the time average velocity is very important to simplify the instantaneous velocity like this. This one also, there's some example of instantaneous snapshot of the problem. This one, and this one is time average. So we can say that the time average have the what we can say the similar pattern to the real one, and we can use the result for the time average. So next we will look at on what is the time average and how we generate the equation for the time average turbulent model. So we look at on what we call Reynolds average Navier-Stokes equation. This one, okay. Reynolds average Navier-Stokes equation, which is we use the time averaging. The time averaging is defined as this one. So the time average is limit from t approaching infinity 1 over t, approaching integration from 0 to t, and properties or x or velocity or whatever. And then this one, basically this one is the pressure that we want to calculate. We have the average pressure, we have the fluctuation pressure as we look at for this. Let's say we look at under pressure. This is the fluctuation pressure P prime, and then this the average P average. So we calculate P prime P fluctuation plus P average. So we can use this one, this Reynolds average pressure to calculate in the simulation. So by using this one, we substitute into the equation, and then we have averaging of the equation in this form. When we expand this equation, we have this one in terms of two-dimensional x and I and j, and at the end of this equation, we have what we call Reynolds stress tensor. Reynolds stress tensor. Reynolds stress tensor basically in the form of where is to go? Okay, in the form of metric number, like this. It has a symmetric metric, second order tensor, and come from averaging convective acceleration in terms of momentum equation from the previous equation. This one, okay, this one, and the expanding of the equation. Oh, where is? How to move to the next slide? Okay. Basically, Reynolds stress provide average effect of the turbulence, or we can say that randomly fluctuation of convection, and of course very highly diffusive, and Reynolds stress tensor represent the combination of mixing due to the fluctuation and smoothing by averaging. Maybe we can say next like this. So Reynolds average, the smooth of this boundary compared to this one, we have a lot of eddy here. So the average, we have a smoothing condition, so that easy to us to simulate and not use the lot of computational time. For the closure problem, from the Reynolds stress tensor, we can use we can model by using two model, which is that eddy viscosity model and Reynolds stress model. So eddy viscosity model is based on Bosnian hypothesis. Reynolds stress is proportional to the rate of strain of time average, and it's proportional constant called eddy viscosity. For the Reynolds stress model, is derived and solved transport equation for each of the 6 distinct real number, see here, or this UV, 6 distinct real number stress plus this dissipation rate of equation. That is the method to or the principle of Reynolds stress model, and compared to the eddy viscosity model. So for eddy viscosity model, we have the dimensional analysis, and at the end we have this kind of what we call that, the eddy viscosity, which is this one is eddy viscosity. And then I maybe move to the other one. No, okay, I just simplify this one. More eddy viscosity, because I will just want to stress out about Reynolds average model. Maybe in maybe not in this slide, but you can look at this one for a while. And this one actually I just want to share with you, which is the tubular model. We have one equation model, call it the Spalart-Allmaras. We have two equation model, which is the standard K epsilon. That's why we call it two equation model. We have kinetic energy equation and epsilon equation. RNG K epsilon, realizable K epsilon, standard K omega, SST K omega. Okay, I think this one mostly you already use in your simulation, but maybe you do not know how to select or what's the correct selection of this kind of equation model. After this, we will look at on what is the purpose or how to choose the correct one for your case. And then from two equation model, we have four equation model. For the four equation model, as I note here, spirit license required for the NC. So this one maybe just for your information that in the Fluent, in the NCs, we still have the equation which is known as four equation model. And we have Reynolds stress model with the transition model, SST and K omega transition model. This one is based on Reynolds average Navier-Stokes equation. We do it average on the again I draw this one. This one, let's say the fluctuation of the velocity. So we do the averaging for the velocity. So all these things we use or we simplify in this model which is that depend one equation model, two equation model, we have Reynolds stress model. And the other one, the other method or the other tubular model known as detached eddy simulation and large eddy simulation. So both of these method, they do not use the averaging or do not use the Navier-Stokes equation, random average Navier-Stokes equation. They use calculate like this, calculate each of the fluctuation in the flow. Okay, so this one, if you look at from this one equation model to Reynolds equation, increase in computational cost per iteration. Similar of this one, detached eddy simulation and large eddy simulation. This one, we need to use more computational cost because they do not averaging. They use each of the point in the velocity or pressure or whatever to calculate the number or the pressure or the properties that we want to calculate there. Okay, so that's all for this video at this time. So the next class we will move on the explanation on each tubular model in the ANSYS Fluent. Start with the one equation model, two equation model, and the Reynolds stress model. So that's all for this video. We meet again in the video or in the class to look at more detail on what is the model that we discussed today. That's all. Thank you very much. See you again.